Liquid level sensors, which measure the height of a liquid in a container, have two classifications, discrete and continuous. Discrete level detectors can only detect whether the liquid is at a certain level. The continuous level detector provides an analog signal that is proportional to the liquid level. Discrete level detectors determine when a liquid has reached a certain level. An application of this type would be determining when to stop the fill cycle of a washing machine. The simplest type of level detector uses a float and a limit switch. There are many possible configurations of a float-based level detector. One is illustrated in Figure A. In this case, the float is attached to a vertical rod. At a certain liquid level, the cam, which is attached to the rod, activates the limit switch. The activation level can be adjusted by relocating either the cam or the switch. Another type of level detector is based on a photocell, as shown in Figure B. When the liquid level submerges the light path, the photodetector signal changes, thus indicating the presence of the liquid. Many liquids, such as tap water, weak acids, beer, and coffee, to name a few, are slightly conductive, which offers another means of detection. As illustrated in Figure C, an electric probe is suspended over the liquid. When the liquid reaches the probe, the resistance in the circuit abruptly decreases. A common use of this sensor is as an automotive low coolant sensor. Continuous level detectors provide a signal that is proportional to the liquid level. There are a number of ways in which this can be done. One of the most direct methods, used in the gas tank of your car, is a float connected to a position sensor. Figure A illustrates one implementation of this method. Another way to measure liquid level is to measure the presence at the pressure at the bottom of the container. Figure B. This method is based on the fact that the pressure at the bottom of the tank, called the head, is directly proportional to the level, as expressed as pressure P is equal to D times H, where pressure is the gauge pressure at the bottom, D is the weight density, the liquid weight per unit volume, and H is the height of liquid in the tank. Now let's look at an example. Calculate what the pressure or the head would be at the bottom of a 10-foot deep water tank. The solution, using the equation just derived, we need to know what the weight density of the fluid is. We know this for water to be 64 pounds per cubic foot. We know the pressure is D times H, which is 64 pounds per cubic foot, times 10 feet, will give you 640 pounds per square foot. This is not a very useful unit, so we need to convert this to PSI, which means multiplied by 1 square foot and divided by 144 square inches will give us 4.44 pounds per square inch. Recall that 4.4 psi is the gauge pressure, which means that the pressure at the bottom of the tank is 4.4 psi more than it is at the surface. The absolute pressure at the bottom would be the gauge pressure plus the ambient pressure, which will give you 19.1 psi because the ambient pressure is 14.7. Looking at an example in SI units, calculate what the pressure of the head would be at the bottom of a 3-meter deep water tank. The solution, using similar methodology, the weight of the water is now 9,800 Newton per cubic meter. Plugging that into P equals DH, we get 9,800 times 3, which will give you 29,400 newtons per square meter, and we know that newtons per square meter is pascals. The gauge pressure at the bottom of the tank is 29,400 pascal. Remember, a litre of water weighs a kg and a cubic meter of water weighs 1 ton or 1,000 kgs. We know G is approximately 10 meters per second as opposed to 9.8. So a cubic meter of water weighs about 10,000 newtons, so the pressure is 10 kilonewtons over 1 square meter, or 10 kilopascals. So 1 meter of water is approximately 10 kPa. Monitoring the weight of the liquid with load cells is another technique that can determine liquid level, looking at figure C. The level can then be calculated knowing the diameter and weight of the tank empty and the density of the fluid. Note that the total weight of the tank is the sum of the weights reported by the 3 load cells. Some devices can detect the liquid level directly. The device shown in figure D is simply 2 vertical electrodes mounted inside the tank. The output of the device, which must be amplified or otherwise processed, is either resistive or capacitive and is proportional to the level. Figure E shows another direct level sensing system. This system uses an ultrasonic range detector mounted over the tank. The complete unit, which includes the transducer and electronics, can be purchased as a module. This ends our brief look at liquid levels.